Welcome again to the virtual summer camp from the USC College of Engineering and Computing. This is the third topic. It's on basically introduction to using computers and software. So it's a very brief introduction to how we make computers do what we want them to do. But we'll start off with some very basics. Computers are really dumb. They do exactly what you tell them to do. And they're comprised of just little bits of information, digital information, which is basically a 0 or a 1. That's how we usually think about it. It's on or off, low or high voltage inside, but it's just made up of millions and billions of these little bits that we can use logic on to make something happen. And that logic is mostly taking part inside the central processing unit, the brain of your computer, that processes instructions, like moving data from one spot to another, or comparing two pieces of memory, is this using and or and other logical comparisons. And there are some specialized things that the CPU can do, like graphics and sound for rendering video games and videos and stuff. It processes input and output. Information going into the computer can come from your mouse, like the location of your mouse, clicks on your mouse, your keyboard, files that are stored on your computer, or information that's out on the internet through the network. It puts out information in form of video or sound, or it writes to a file, or it even prints stuff out to the printer. So that's input, output, processing information. That's the basics. You got to understand something about hardware, I think, to understand computers and how they work. So your CPU is the brains. It's a small chip typically. On a desktop or a laptop, it can be a pretty big chip. But inside your cell phone, it's very small, and it has some memory. The L1 cache is right there. It's the easiest to access memory. L2 is usually on the CPU, but it has to go a little bit further and spend a little more time getting any information out of the L2. So server chips for big computer servers, like a web server, would have lots of cache memory because it helps put things very close to where the memory needs to be to access it. There's read-only memory. That's your BIOS. So when you boot up your computer, that is holds the operating system that tells everything how to work together. There's random access memory and hard drives. Random access memory is like it's another volatile memory where the computer can go if it needs to store some information. Hard drives are the same thing. Hard drives are resilient. Disk drive or a solid state disk drive will keep information for longer term and will be there when you reboot. But the CPU basically, all the stuff in memory and RAM and the CPU will be gone when you reboot, generally. A lot of times these days we'll have a separate graphics card, which will be hooked in through a bus. You can replace your graphics card if you want a better video gaming experience. They call it graphical processing unit. It's not exactly a general purpose processing unit. It's very highly optimized to render triangles and show you pretty pictures when you're running around shooting stuff in Fortnite. And there's a lot of random access memory specialized for video RAM, and it connects the output to your monitor. There's other chips for your USB, like your keyboard peripherals, or maybe a sound chip to deal with speakers, or it might just run through USB. Your network interface could be USB, or it could be actually hooked in and hooked up to the outside. So all of this computers all takes place inside your laptop or inside your desktop. It's all hooked together. There are differences in hardware. A PC is not the same as old Macs or Unix machines. They were totally different. You couldn't run programs on each one. These days, they're a lot more common, or there's a lot more overlap. A PC and a Mac these days run on the same hardware, and a lot of Unix machines run on the same kind of hardware, same kind of chip. The biggest difference in chips these days is between desktop, laptop, and mobile hardware. They are very different. There are lots of different types of chips, but like I said, the desktop machines, laptop machines are getting to be pretty much compatible. Mobile hardware is not as compatible right now. There's a lot of differences there. There's a lot of differences in operating system. So you can run lots of different versions of Windows. There's every few years there's a new version, it seems like. On the Unix side, there's a class of operating system. Apple is actually, their operating system is based on Unix. Linux and other Unix, even Android, these are all Unix variants. The operating system is the low-level program that controls how programs execute and how components talk. So the operating system is the program that runs right on the hardware. So it's in charge of running other programs basically and dictating how you write files, how you access memory, how the programs work. So you have different operating systems that limit what you can do or control how things work together and what hardware you can use. The processor and memory and storage. When we're thinking about processors and memory, these are really processors have grown over the years. You can measure millions of instructions per second. And the first PC I ever used years and years ago in the 70s had less than 1 million iterations or instructions per second. It couldn't do too many calculations. But about every 10 years, I've got a list here now, over the last 40 years, now we've grown. In 10 years, we went from 0.7 MIPS to 11, and then we keep growing by factors, crazy factors, so lots more instructions. The random access memory, how much memory does it have access to, has grown from 0.03 megabytes to thousands of megabytes potentially over the years. And storage is long-term storage. Early hard disks were pretty small, maybe 20 or 30 megabytes, and now we have we usually have hundreds of gigabytes, if not multiple terabytes. So that's 4,000 gigabytes in a 4 terabyte drive. That might be 4 million megabytes, so from 30 to 4 million. So it's just crazy how things have grown. And there's something called Moore's Law you can look into that dictates how computer architecture, the number of instructions ratio for price goes up every 18 months, I believe. So what is a program? A program is something that does stuff on your computer, and they're built from source code typically, so a text file full of instructions that dictates what your data types are. Do you have integers or characters or real numbers or arrays and matrices, different structures? How do you put your data together inside the memory, inside the computer, in the program? You have statements, you can run functions, you can do math functions, you can run a function like find the maximum value in a vector. Relational operators for doing true false comparisons. Is this variable less than this variable? Is this variable less than a number? Are these exactly equal? Logical operators, ands and ors. Conditional statements, if statements, like if this, then do something else. Loops, if you want to do something over and over, or loop until some condition is met. So source code, your program, involves these kinds of pieces of information. And the specifics differ from language to language, but the concepts are all very, very similar. And a lot of times you'll have a variable name that relates to something in memory. So here we have a variable named K. It could be variables A and B. So these variables are in the memory. There are different types of programming languages. So you have compiled languages where you have a program that makes a new program. It reads a text file, it reads all the language rules for C or C++ or Fortran to convert that code into an executable. And it usually runs pretty rapidly, but it only works on the target operating system. So if you compile some C code to run on a PC, it probably won't work on a Mac or an Android phone. There are some ways to get around that, but in general, it's specific to the operating system. There are interpreted languages as well, like Java. You compile it, or you have to have a special program. You have to run Java to run a Java app, or you have to run MATLAB or MathCAD to run a MATLAB program or a MathCAD program. They don't run natively, so basically the Java or the MATLAB or the MathCAD becomes an interface between your program and the operating system. And these used to be sort of slow, very slow, but computers have gotten pretty fast, and the compilers, the just-in-time interpreted languages, have gotten better. So MATLAB's a good bit faster. There's not as big a difference between straight compiled code and interpreted these days. Now, I want to talk a little bit about using flowcharts to represent a program or a problem solution method. So an algorithm is a fancy way of saying how you solve a problem, how you manipulate data. Flowcharts are simple graphical representations of our methods, and that's a lot of times engineers love to have flowcharts because they help you solve problems and they help you organize mentally what the steps are and graphically, when you trace through a process. And if you have basic input and output data, you put it in this kind of shape. Travis, if you want to get input in, you ask a question, how many apples? We're going to ask the person, the user, how many apples do you want? And you put that in variable A. Or you read a file name. You read the whole file name, you put it in this string. Or you print out something to the screen and say the number's got to be greater than 0, or you plot some values. So these are different examples from something like MATLAB, where you have a single line of input or output. Basic math statements or function calls would be in a rectangle. So if you want to take a variable I and increase it by 1, you could do that. If you want to take two variables and add them together and stick them into the variable sum, or run a function like max, where you look at a vector and you get the maximum value and stick it in a variable A, or you take some input on your function and you run it, whatever function you define, and you put the output in a new variable C. So this is a pretty standard way. The stuff on the right happens, and whatever the result is, it gets pushed into the left-hand side. That's one way of, a lot of languages will use a simple statement to do something at one iteration or one point in the code. Conditional statements are if-then-else statements. You come in and you check a condition. If it's true, you do one thing. If it's not true, you do another thing. So it's called a branch in your execution flow. You move from one thing to another. In an if example, so this is the code. This is what the code would look like for most, in like a MATLAB. You get the input, you do the current year, so you do a little math, and then you have an if statement, and you either print you can vote or you can't vote. So graphically, you might have the different shapes where you go from input, run a function to get the variable now value, compare these two to get age, compare age to say true or false. If you're greater than 18, you can vote. If you're not, you can't vote. And that's a simple example of some people, until you get used to looking at code, writing things out in a flow chart can be beneficial. It works for small, simple things, at least to get your head wrapped around what's going on. It helps you visualize something, I think. Another concept is called a variable trace. So variables have to have a value. Initially, if they don't have a value, they call it null. They're just not assigned. So initially, there's no value, and you can run into errors if you try and use a value that doesn't exist. Some languages will have a default value. I think MATLAB might default to 0 when you make a variable. But I think if you compared, depending on how you run it and how you compare it. So in this case, you go through each step in the program and you trace the variable value. So at this point, the variable A may have your year that you were born, and the other variables don't have value. So the next thing that happens, you get the current year, and after that executes, this variable may be 2015. This is old slides. So you have a year, you have this year, you do a little math, and now the age has a value. So those are the three variables, and as they change over time, at each point as we go through execution of a computer program, those variable values are going to change. And that's one important part. A lot of times you have to visualize or think about how the variables change in your program, and that's how you track down problems in your program. Another concept is called pseudocode, where you don't really worry about how the computer is going to work, syntax or details. It's like an outline for a paper. Have the basic structure there, like what you want to do, and like getting your input data may be like a whole program in itself. It's a higher level sort of summary of what you need to do. So get your data, check it. If it's consistent, compute the results and display the results. Otherwise, stop. So that's the high level. And each one of these could be broken down further. So each step could have its own pseudocode again, and then you actually get into organizing and running stuff. There are different types of data, true and false values. In MATLAB, they use 0 as false. I think 0 and negative is false, and 1 and anything positive is true, but basically 0 and 1. Integer values, a lot of times they're limited in range. You can't have every single integer in the universe. So depending on the computer program you're using, there may be some limit. Floating point with sine, exponent, and mantissa. And there's a limited accuracy. Like you can't have every single exponent out there. So because of limitations, your mantissa has limited accuracy and your exponent has limited accuracy, depending on how many bits you're using. And it's pretty accurate, but there's still a limit to everything. You can have specific characters. You can have an array, which is like a vector. It's like a list. It could be a list of characters, could be a floating list of numbers, list of integers, list of Boolean values. And there are more complex data types like objects. So objects would be like a single variable that has a variety of data affiliated with it. Like you could have a variable for a person, they have a name and they have an age and address, telephone number. So you have one variable that has these other bits attached to it as a single structure. That's a little more advanced. But the basics are integer. For most of the stuff we do for computation, it's going to be integer and floating point. Sometimes we use characters, but mostly numerical stuff in lists and matrices. So when you have a statement, a lot of times there are built-in functions like min and max to find if you have a list of values or a vector, an array, find the minimum and maximum value, floor and ceiling for math, modulus, power, math functions, sine, exponent, length of a vector. Some computer programs don't have a length function. You have to keep track of how long. MATLAB is nice because you can say, well, I don't know how long this vector is. I can ask for the length. You can write your own specialized functions, like if you want to have a special average function, you can make your own, and that's one of the powers of computer programming. Your conditional statement is basically check a statement and do something. If this is true, then you print out. If it's not true, you print something else out. So you have two options, either this or this. If this is true, then the else. If it's not true, the else will occur. And everything typically follows PEMDAS. Please excuse my dear Aunt Sally order of operations. Now, if you're worried about something and you don't know exactly if it's going to work, I always say just put more parentheses in there to make sure it does exactly what you want it to do. So in this case, check x minus 1, is that less than 0? Check x times x, is that less than 0? If both of these are true, then it's going to be true, the overall statement. So that's what I mean by putting more parentheses in. And maybe sometimes if you don't trust your assessment of PEMDAS order of operations, you may want to put a bunch of parentheses. A for loop is important if you know how many times you want to do something. So if you have like a vector, going into the loop, you know exactly how long that vector is. So you can say for every element, basically for every element in this length, in this string of numbers, I'm going to print out the value. And this is a way of accessing the ith value. So I is going to change from 1 to 2 to 3. It's going to print out the first value, the second value, and the third value of x. And x has a value of 7 and 8 and 9. So it's going to go through 3 times and go 7th and 8th and 9th. So that for loop goes back and forth. This print statement goes through, in this case, 3 times for every value of x. So loops through, you know how many times to do it, and it does one thing every time for 3 values. The variable I changes from 1 to 2 to 3, and this is how it's counted. A for loop might look like this in a graphical representation. So each line of this little piece of MATLAB code would have set up a vector, calculate the length of that vector, push that into the variable a, set up a counter I. So you print the ith value of x. So you have a vector x, and I is going to change from 1 to 2 to 3, and then you increment I up by 1. And as long as I is less than a, you go back and you print it and increment again, and eventually it's not less than a, it's equal to a, and it stops. So when I is equal to 3, you're not going to go through again. Is that right? That might be a mistake. I have to check that. No. Oh yeah, it's going to go back when it's 3. So it's going to go through when 3. This is going to increment to 4. 4 is greater than 3, so it's going to stop. So that makes sense. So that's correct. Good. So your for loop, again, a variable trace. You set up x, you get a value for a, and then it's going to go through. You can do 2 things inside a for loop. So it's going to print the counter I and print the ith value of x times itself. So it's going to do 2 steps. So again, we have 3 iterations of this loop. The first, second, and third iteration. I is going to be 1, then 2, then 3. And the first value of x squared is 7. It's 7 times 7, and 8 times 8, and 9 times 9. So it only iterates 3 times, but it does 2 things each iteration. And for loops are amazing. They can be used to solve really hard problems in a lot of cases. A while loop is like a for loop, but different. If you don't know how many times it's going to loop, use a while loop. The while loop has to basically converge, has to stop. And sometimes you get in trouble because you have a condition that's never met. So if you, in this case, you put in a number, enter a number greater than 100, and you have a value I, and it's going to double until that counter I starts at 1, then it goes to 2, then 4, then 8, then 16. It's going to keep doing this until it exceeds A, and then it's going to stop. So you could potentially get yourself in trouble with while loops because sometimes they don't stop or they have no end condition. Again, if you want to make a flow chart for a while loop, this is a simple piece of code that prints something until you have some condition. So basically, you enter a number. If, what are we doing here? This is not a very good example. We'll skip this one. Is it? Yeah, this is not a good example. Well, let's skip that one. So we can do multiple things inside a for loop or a while loop. Same way, you can have multiple things that happen inside a for loop. And there's something called nested. You can put a if inside an if statement or a for loop inside a for loop. So you can nest your statements. And for this guy, what's going on here? If x equals 6, and then we say is x equal to 2, is x greater than 2, and that is true. If that is true, this code is going to happen. So that means we take x and we multiply by 4 and we get 24. So I say D, and I'm right. This code will never happen as long as this is true. When x is 6, it's going to only execute this first line. So this is going to replace the value of x with 4 times its original value. This is a for loop, and it's going to go, the counter j is going to go 1, 2, 3. I'm just going to set up a value. The first time through, the value on the right hand side is going to be 11, and then it's going to be 12, and it's going to be 13. And it's going to put 11 into the one element, so that looks like this is right. And then it's going to put 12 in the second element and 13 in the third element. So I'm saying D again. Here's a for loop, a little more confusing. What's the result of this code? We have sum, this is 0. We start off initializing sum to 0. We have a vector of values, 4 values. And this counter is going to go through all 4 of those values from 1 to 4. It's going to take the current value of sum, and it's going to add to it the ith value, or the jth value of x. So the j is going to be 1, 2, 3, 4. So the first time through, sum is 0, and xj is 4. So sum is going to become 4. The next time through, sum is 4, and x, the second value of x is going to be 3, so sum is going to become 7. So after that, we have the third value of x, which is 5, and sum is 7, so we're going to get 12. And the fourth time through, we have j equals 4, so x4 is 2. We're going to add that to 12 and get 14. So I get C, because it iterates each time through, increasing up by this amount. And you can trace through that value for sum over and over and over for those 4 steps. I mentioned earlier there's a nested statement. If you have an if statement inside an if statement, and it's sort of key to recognize that if this is true, if this A is greater than 0, the inner part can execute, and you sort of indent it in because this section of code only happens if A is greater than 0. So then you're going to check the modulus of A divided by 2. So the modulus of A and 2, if that's equal to 0, it's a positive even number. If A is greater than 0, but not modulus 2 equals 0, it's a positive odd number. So if this is not true, the only other cases can be down here. A must be a negative number or 0. So as long as you have an integer as your input. This is what it might look like in terms of code here for a flow chart. You get an integer, you check one value. You can notice that when you have nested if statements, it starts to be very confusing for your flow chart. So flow charts are the best tool, but sometimes it can help you if you think a little bit graphically to start to represent what's going on, so you can trace through the different parts of your algorithm or your program. So this is if this is true, this is the other if statement. We have the first if statement, and when it hits true, you move to the second if statement. And you have your three different conditions, three different outputs that can end up being. A lot of times we use a nested for loop, and this is when we're dealing with like a matrix of data, which is a two-dimensional array where you have rows and columns. If you think about a pixel on a TV screen, you can index every row and column value with an element. So the XY graph on your computer screen has a row and column value for data. You actually have 3 pixels for every pixel. You have a red, green, and blue value. So you have actually 3 numbers for your matrix of values on your screen. But for right now, let's just pretend like we only have a two-dimensional array with a single value for row and column. And if you go through, if we have 2 rows, so we have to go through every row, and we'll start with row 1, and then we have to go through every column, and we have 3 columns. We're going to access the row and column value. So when row is increasing, row is going to be 1, and then column is going to increment 3 times. So column goes 1. So the first time through, you've got row and column equal to 1, so you can evaluate this line, and it basically puts a value of 1 in this first element. And then column goes to 2 and then 3. So the third time through, row is still 1, and column goes to 3. So we have 1 times 1, and 1 times 2, and 1 times 3. And those are going to be stuck in the first row, the first column, second column, third column. When you're done with that inner loop, now you get to this end, you go back and row increments. So when row increments to 2, the inner loop starts to execute again. It goes 1, 2, 3 times, changing column. So these guys are going to change. 2 times 1, 2 times 2, 2 times 3. And we end up having a 2 by 3, 2 row, 3 column array with these numbers in the elements. So this is a nested if statement. Let's think about it. Y equals 3 initially. Is y greater than 0? That is true. That means this is going to happen. That means this is not going to happen. And so we have to check this if statement. Is y greater than 2? That's also true. So this is going to happen. I'm going to take y, and we're going to add 1 to it. So it should be 4. I got C. So y is greater than 0, so we can make this first condition. It's greater than 2, so this condition. This will never happen with this value of y, just like this will never happen with this value. The other conditions won't be met. A double for loop. So we're going to, this is my, looks like this is my row, J is for my row, and K is for my column. So it looks like I have 3 columns and I have 4 rows. So it's going to go through the first row, 3 values, boom, boom, boom. And then it's going to change the J from 1 to 2 and to 3 to 4. So it should be 4 rows, 3 columns. It's going to be a matrix or a two-dimensional array. So my X variable starts out, there's one way to initialize a variable is nothing. 0 by 0, no rows, no columns, no values. So set it up to be an empty value in MATLAB. And then this is going to execute 12 different times to put things into my matrix. I'm going to take the J value and the K value and stick them into X at different locations. So the first row, the second row, the third row, the fourth row. You can always make up your own functions. You can define whatever you want to do, like a special average function, or you have to generalize it to take whatever data and process it and spit out an output. So it could be a short vector or a long vector, or you have to know what assumptions you're making. Maybe you're assuming the data always comes in a certain format, like it always has 20 elements. So functions can be very powerful, but they're a little frustrating sometimes to set up. Now, something you do in a math class, you might set up a function, a mathematical function. You'll learn about this one, or you've seen this one. You want to find a value where that function goes to 0, or it crosses y equals 0. So if you have this function, it changes as a function of x. That function may have a value for x, lower and upper bounds on x. And if you know one side is positive and one side is negative, and you have a continuous function, you know it's got to cross f of x equals 0. So if this is a positive number over here and there's a negative number, you know there's at least one 0 crossing somewhere in between. So the bisection method says, okay, you have a lower bound on x, take that lower bound and upper bound, look at the middle value. If you look at the middle value, oh, this middle value is negative, so we can throw away the upper value and squinch in, and now you're looking only between these two. So you're only looking over this range. You know, one end is positive, one end is negative, so there's still got to be a 0 crossing somewhere in there. If you do that a few steps, usually you can find the value where your function crosses 0. So here's a pseudocode. Get your lower and upper bounds, determine the midpoint, find the function value at those lower, upper, and middle values. As long as the middle point is, if you take the value at the middle point and square it, that's going to be a positive number. As long as it's bigger than some small number, keep doing it, assuming your logic works. So if your functions, if f of xl and xm are both the same, you're going to move the lower bound up to xm. Otherwise, you're going to move the upper bound down to the middle point. So it's basically, you either bring in one side down, or you bring the other side up. So you're going to converge eventually when this condition is met. A lot of times, if you're writing code, you may want to check, because if you may want to make sure you start off your problem or your program or your data is consistent. We assume that the function values, if they're both positive or negative, that means there's no 0 crossing with your starting point. So that would display an error message and quit. You have to, if you want to be a little better at things, you need to check common errors that might occur to your data or your inputs. One of the tricks to writing programs is debugging. You were going to make errors. Nobody is perfect. Very few people are perfect. So you have to go through your procedure, your program step by step, and think about what variables or what possible values they could take. I like to put print statements in to figure out what's going on at each step. There's better tools these days to trace variable values and stop at a certain point in your code. I like to get something working and then build that to make it more complicated. You can do smaller cases, and so maybe you just test the first 2 or 3 iterations instead of doing processing all of your data. Just process a little bit and make sure it's working and giving you expected results, and then turn it loose on a larger data set. There's a whole lot of information about variable names, balance between long and short, clarity. A lot of people use I for counters, but you could use like first loop integer counter. Some people like to use this combination of upper and lower case letters. There's just lots of different options out there. Just be consistent, and probably most important is put comments in your code, which means text that is not real code. Like, what is happening here? What am I trying to do? So that it will, later on, if you come back a week later, you might not remember what you're trying to do. If you're trying to fix or modify something, having a comment there can help you out. And there's something called edge cases, where you imagine weird ending cases, like what happens in the last time through this loop. So the edge cases sometimes are where things break. Now, speaking of computers, there's a lot of different majors, especially at USC, that you can go into. Software engineering is something where you look about software, developing and building industrial software or software for problems. We have a master's degree in software engineering at USC, but not an undergraduate. Computer engineering is more focused on hardware, so the interface of electrical engineering and computer science. So you do more with, it's like electrical engineering specifically for computers, but you still have to know some software because you have to be able to make the hardware do things. Computer science is a more general study. It enables the use of programs to do information processing. So it's a more science, instead of, you will learn to do programming in computer science, but it also includes some higher level math and analysis, more scientific instead of technology based, if that makes any sense. Computer information systems is a business application area, and that's another it's not as general as computer science is pretty general, but computer information system is more about business applications, and integrated information technology is more system administration. So they're all different shades, very related. You have to understand some hardware no matter what. You have to understand some programming no matter what. So all of these are very related, but they just depend. Honestly, part of it that sometimes influences our students, computer information systems and IIT, I think those majors, you can use business calculus. So the level of math required is different for some of those. And some people don't like doing math, so you might not want to go into computer science or computer engineering. I think those require a little more mathematics. Computer science actually has a pretty rigorous math. I think it might require even more math than computer engineering. So they're very similar, and they can work in similar fields and similar companies, but they have a little bit more specific application, specific classes. But you need to understand computers, hardware, and software for any of these. Today, I'd also like to mention Scratch, which is a nice software from MIT for teaching how to do programming. You basically, instead of typing out code like in MATLAB, you attach blocks together and it looks pretty much like real code. The good thing about that is you don't have to worry about making a syntax error. Like if you forget a comma or a space or a semicolon, a lot of times it'll break a computer program. But it's hard to make those kinds of errors in Scratch. You make logical errors because you do something dumb in Scratch. It teaches transferable coding skills. So if you learn about for and if and while statements work, those, they work in Scratch, very similar to everything else. So those concepts, running a for loop or an if statement or a nested if statement, those are that's very useful and will help you in Java or MATLAB or C or anything pretty much. It's an online community, so you can look at other people's projects and learn from what they've done. And it's great for games and animations. I had my daughter making penguin animations when she was 5 or 6. My son was making helicopter games about that same time. But I still mess around and make dumb games occasionally because it's pretty easy to make simple two-dimensional games that look okay and they're actually sort of fun to play. This is the interface. You start up Scratch. They have a display where stuff moves around, and then you have sprites, individual graphics that do things and have behaviors. Those behaviors have code that you can piece together, like movement or size or changing colors or whatever. Sprites can also change their costume, so you can have multiple switches between different costumes for your sprite. Some of the suggestions: always use vector graphics, not bitmap. So the Scratch Cat, if you use a bitmap version, you can see how it's pixelated and ugly. It may look okay on a small screen, but when you blow it up full screen, it's going to look garbage if it's bitmap. You may want to look into other projects to see how they work. You can look into somebody's project, and there's a thing called Remix where you copy their project to your account, and then you can change the artwork and just use their code, or you could take their artwork and make the code work. I like to do a little and check and see what it does. So get something to work and then add more complexity. So get something moving and then get something moving better and then get something doing something else. Some of the advanced topics out there to learn if you're already a Scratch expert. Using clones, I think that's an interesting thing for doing like shots or trees if you want a lot of something pretty easily. You can make your own functions. They're called my functions to simplify your code. And you can use messages for timing events to coordinate. I've used that when you're switching between like start screen. If you want to make it more like a game, you have a start screen and then you have the game, and you alternate between the ending screen, start screen, the actual game, and the ending screen, and then you go back to start screen. And you can use multiple starting blocks for a single sprite. So there could be basically multiple programs or behaviors for a single sprite happening at the same time. So you might have one thing that basically is controlling movement, and then another when clicked area that's controlling whether or not, trying to detect whether or not you're getting shot. So there's lots of advanced stuff you can do to make it more interesting. The tutorial is in a PDF, so you can switch back and forth between it on the screen. And it should step you through the first cat and mouse game line by line. The second tutorial, it doesn't have every single step described. It's basically a space war game where you have to do the graphics yourself. You have to draw the aliens and the ship, and you have to do a little more of the advanced stuff, the my blocks and cloning and vector graphics. So the first one is just getting used to Scratch, the interface, quick cat and mouse game. The second one is a little more involved, and the tutorial doesn't tell you every single step of the way. So try doing both of those tutorials, and there's a million other tutorials for Scratch out there. I think it's a great tool to learn about programming if you have time to play around and make some video games. And that's it for today for this first part, Basics of Computing and Introduction to Scratch.